What if the laser, one of the most recognizable technologies of the modern age, began with light that nobody could see? Its first ancestor was not a beam crossing a laboratory, but a microwave device built to amplify invisible radiation. The path from that obscure machine to a sharp red flash in 1960 passed through theory, skepticism, rivalry, and one deceptively simple ruby rod. The key idea was stimulated emission, a process predicted by Albert Einstein in which an incoming photon can prompt an excited atom to release a second photon with matching energy and direction. Instead of light scattering randomly, the emissions reinforce one another. In principle, radiation could be amplified. In practice, the conditions seemed extraordinarily difficult to create. During the 1950s, Charles Townes pursued that principle at microwave frequencies. His device became known as a maser, an acronym for microwave amplification by stimulated emission of radiation. A maser did not produce visible light. It amplified microwaves using carefully prepared molecules and a resonant chamber, an enclosure that encouraged the right waves to build upon one another. The maser was a crucial proof that stimulated emission could be turned from an equation into an operating machine. Yet its success created a more troubling question. Could the same logic work at much shorter wavelengths in the region of visible light? Light oscillates at far higher frequencies than microwaves, and controlling it would demand a new kind of precision. Townes and Arthur Shallow confronted that challenge in theory. Shallow, a physicist working with Townes, helped develop the framework for an optical maser, which would eventually be called a laser. Their proposal described how mirrors could form an optical cavity, reflecting light repeatedly through an active material so that selected emissions gained strength. The concept depended on population inversion. That term describes a condition in which more atoms occupy an excited energy state than a lower state. Normally, matter settles toward lower energy. A laser must temporarily reverse that balance. Only then can stimulated emission outpace absorption, allowing an organized beam to emerge rather than a weak glow. On paper, the architecture was elegant. In a real laboratory, it was another matter. A useful optical device needed a material that could be energized efficiently, release the right wavelength, and survive the process. It also needed mirrors aligned with extraordinary care. Researchers could imagine the mechanism, but imagination did not guarantee a working instrument. The debate became sharper because visible light amplification seemed, to some researchers, impractical. The theory was persuasive, yet the engineering obstacles were severe. A material might absorb its own light. Energy might spread into heat. The atoms might refuse to remain inverted long enough for amplification to dominate. The first laser was hidden inside a thicket of conditions. That uncertainty opened a space for Theodore Maiman. At Hughes Research Laboratories, Maiman approached the problem with an experimental style that was direct and pragmatic. Rather than beginning with an elaborate apparatus, he focused on finding a workable combination of active material, energy source, and optical cavity. His active material was a ruby rod. Ruby is a crystalline form of aluminum oxide containing small amounts of chromium, and those chromium ions provide the energy levels needed for laser action. The rod was not valuable because it looked beautiful. It was valuable because its internal structure could absorb intense light and later release energy in a more organized way. The energy came from a flash lamp, a powerful source of brief bursts of light. Maiman arranged the ruby rod and the lamp so that the ruby could be intensely excited. Mirrors at the ends of the rod helped return light through the crystal. One mirror reflected nearly all the light, the other allowed a portion to escape. That escaping portion was the essential event. Inside the ruby, photons stimulated further emissions. The mirrors sent them back through the material. Each pass increased the opportunity for amplification. When the gain became greater than the losses, the system crossed a threshold, and a coherent beam formed. Coherent means that the light waves maintain a strong, orderly relationship with one another. The machine was hardly the universal tool people now associate with lasers. It was a first version, built around a ruby rod, a flash lamp, and a carefully arranged pair of mirrors. Its output was pulsed rather than continuously sustained. Yet that limitation made the achievement more revealing, not less. A technology can begin as a narrow demonstration before becoming a civilization-wide platform. In 1960, Maiman produced the first working laser at Hughes Research Laboratories. The result answered the question that had unsettled the field. Visible light amplification was not merely a theoretical extension of the maser. It could be made to function in the laboratory. The achievement did not instantly settle every dispute. Recognition was complicated, and the laser's importance was not immediately obvious to everyone. Early reactions reflected a familiar pattern in technological history. A device may be undeniably real while its future uses remain difficult to imagine. The first laser did not arrive with a complete application list attached to it. Its significance lay in the principle it demonstrated. Light could be generated with unusual direction, narrow spectral range, and coherence. A conventional lamp spreads radiation across many directions and wavelengths. A laser concentrates energy into a far more disciplined form. That discipline would later make possible applications far removed from the original laboratory problem. The maser had supplied the conceptual bridge, but the optical version required a different experimental temperament. Towns and Shallow clarified the route. Maimon found a practical vehicle. Their contributions were connected, but they were not identical. One story belongs to theory and architecture. Another belongs to material choice, construction, and the stubborn test of an actual pulse. That distinction matters because inventions are often described as if a single flash of insight creates the finished technology. The laser was not born fully formed. It emerged from an exchange between prediction and resistance. Equations identified a possibility. Laboratory materials imposed conditions. Engineering reduced those conditions to an arrangement that could survive contact with reality. The ruby laser also exposed an unexpected lesson about future technology. The winning material did not need to be exotic in appearance. It needed the right atomic behavior. The decisive breakthrough came from understanding how impurities inside a crystal could act as the active centers of amplification. At the macroscopic scale, the device looked simple. At the microscopic scale, it depended on carefully managed energy transitions. From that point, researchers began exploring other laser materials and designs. Some produced different wavelengths. Some operated continuously. Others delivered short, intense pulses. The original ruby system was no longer the endpoint. It became a reference point, a working demonstration that encouraged an expanding family of optical technologies. The beam's unusual properties soon connected it to fields that had not shaped the original invention. Lasers could measure distance, carry information, read encoded patterns, guide surgery, machine materials, and support scientific experiments. Fiber-optic communication would eventually use light to transmit vast amounts of data through thin strands of glass. The practical world began to inherit an idea born in a debate about stimulated emission. Yet the deeper transformation was conceptual. Before the laser, light was often treated as illumination, a means of seeing. After the laser, light could also be treated as a tool for precision, measurement, communication, and control. The invention did not simply create a brighter source. It changed what engineers and scientists believed light could do. The origin story therefore contains a productive paradox. The first laser was both revolutionary and rudimentary. It used sophisticated quantum principles, yet its physical form was comparatively plain: a ruby rod, a flash lamp, and mirrors. Its power came not from complexity alone, but from arranging ordinary components around an extraordinary understanding of matter. Charles Towns supplied the Maser foundation. Arthur Shallow helped articulate the optical extension. Theodore Maimon assembled the first successful working laser at Hughes Research Laboratories in 1960. None of these steps erase the others. Together, they reveal how breakthrough technologies are actually made. A prediction opens a door, a skeptical community tests it, and an experiment finally turns possibility into evidence. The laser began with invisible microwaves and an argument over whether light could be amplified at all. It became a controlled beam, then a scientific instrument, and eventually an invisible infrastructure beneath communication, manufacturing, medicine, and research. The original flash was brief. Its consequences were not.